So let me summarize what I have up on the board here for you. This should be familiar. This is stuff I wrote down last time. If you ever want to switch between the linear world, the old stuff, and the angular world, where we talk about everything in terms of angle, you can do that. It's very straightforward. You basically just need a third ingredient, which is the radius of the circle that you're making. So if you want to go from how much angle you've covered to how much distance you've covered, so you put the angle in radians, you multiply by r, you'll get the distance in meters. If you want to go from angular speed, how much radians per second you're traveling, you multiply by r, you'll get meters per second. And finally, if you want to go from angular acceleration in radians per second squared, you multiply by r, you'll get a tan in meters per second squared. Now remember that a tan is the part of the old acceleration that controls your speed. There's another kind of acceleration, a centripetal, which is not at all mentioned in the angular world. And the reason why is in the angular world, a centripetal has no counterpart. In the circular world, you're already assumed that you're moving in the circle. But in reality, we know that you can't move in a circle for free. A centripetal is required. And really, a tan and a centripetal are really just components of one actual acceleration. Okay? When you are doing these, make sure you use sizes only, because the sign usage in the linear and angular worlds are so different that you can't reasonably expect a sign to come along. So whether or not the absolute value signs are explicitly written, do not include any negatives in this batch of stuff. The other thing I mentioned last time was that what you can do is you can sub in and show that the constant angular acceleration equations are literally just the constant regular acceleration equations with everything replaced by its angular counterpart. So we have these bizarro versions of the acceleration equations we've had before. What I've done is I've replaced delta x with delta theta, I've replaced v with omega, and I've replaced a with alpha. Those work exactly the same as before. We have 5 equations. Each of them is missing one of the 5 variables. We use the same problem-solving strategy, which is we need a minimum of 3 things. Then we can solve for a 4th. We don't know, don't care about a 5th, because we pick the equation that avoids it, right? Remember all that stuff? Same ideas? And these, we do want to make sure, just like before, that we have signs upon the input and the output. So we'll put in everything plus if it's counterclockwise, minus if it's clockwise. We'll put its signs on input, and when we get a sign on the output, it likewise means something. If we get a plus on the output, it means counterclockwise. If we get a negative, it means clockwise. That's our entire toolkit, and I want to throw it all at an example problem, which is meant to have pretty much everything you're asked for on the homework at any point. So let's go ahead and do an example. In fact, let me actually move it a little bit over this way, give myself a little more space. So what I'm going to have is a car, and this car is going at 20 meters per second, and it's going around a turn, and it's slowing down while it's doing so. So you may have experiences, you're taking a curve and you see something ahead and you have to slow down. So by the time it's completed a half circle, it's going slower. So it's going in a circle and it's going slower. I'll say that the radius of the circle is 10 meters. So basically my givens, these are my givens. My initial speed is 20 meters per second. My final speed is 5 meters per second. That's a half circle later. My radius is 10 meters. And let me also give you that at least you have a steady foot on the brake. You're going to smoothly connect these two velocities, okay? So you have a smooth transition. Smooth braking. Now when you see that, that's your code word for, of course, constant acceleration of some kind, right? So you're going to smoothly connect your 20 meters per second to 5 meters per second. You're not going to come to an abrupt halt sooner than you have to, or do it in kind of a herky-jerky manner and make your passenger's car sick, okay? So, let's ask some questions about this. In fact, let me throw a whole bunch of questions. Let me find the time it takes. How long does it take for me to accomplish this braking? On the angular side, I want to find, well, basically everything that I can. Omega initial, omega final, alpha. On the linear side, let me find the magnitude of A tan. So I'll write that without a vector hat. And then let me find A initial and A final. And those I will include a vector hat, which means that I'm interested in direction as well. So that's a good bunch of stuff. That might not be every single last thing, but that's almost everything for sure. And we can go ahead and do this. So first of all, smooth braking, that implies I have a constant angular acceleration, okay? So I'm going to slow down as I'm going in a circle. Smooth braking is code for that. So what I can do is, of course, use my constant acceleration equations on the angular side. So let me go ahead and put down these guys in no particular order. As we've traditionally done in these equations, we've just left off the vector hats there, but that doesn't mean that signs aren't important. Remember, as I've pointed out here, signs go in the input, signs go on the output, okay? So, first of all, let's start with the angular displacement. What should I pick for my angular displacement? Pi. Why pi? It's half a circle. Now, is it a counterclockwise or clockwise circle? Counterclockwise. Should I put plus pi or minus pi then? Plus, right? So everything goes in sign. The plus is counterclockwise. Now that's just one thing. Of course I need a minimum of 3, but I basically have that because while I'm not given omega initial and omega final, if I'm given their linear counterparts, finding those is as easy as going from linear to angular, right? So if I have the rotational version, I can easily get the linear version. If I have the linear version, I can easily get the rotational version, right? So let me go ahead and do that. I know that V equals R omega. So at any particular moment in time, if I know the meters per second, I can get the radians per second or vice versa. Now in this case, I'm actually looking to go over to the angular side, so let me go ahead and solve. Looks like this. I can use that at any particular moment, so I'm going to use it twice. Let me use it for the initial moment. So if I know the initial speed, I can get the initial angular speed. So I know that initially I'm going 20 meters per second. I'm doing that in a circle of 10 meters. So 20 divided by 10, that's 2, right? And then notice that the meters cancel with the meters. So then I just have my radians, it's a fake unit anyway, it just appears to hold the place of the units in the numerator. And then of course I have the per second still there. So remember, radians is a fake unit, so if you don't have anything else to hold the place of the units in the numerator, just throw it in. Likewise, when something else slides in, you can kick it out. That's the beauty of radians. It's not a real unit, so you can throw it in whenever you want. Okay? So that's the initial angular speed. And which direction is it? Is it counterclockwise or clockwise? It's counterclockwise. So if I wanted to throw a vector hat on this, I should properly say this. So that's my initial angular speed. The plus is counterclockwise. That's what plus means in the rotational world. I'll go ahead and throw that in here. That's plus 2. And even though I don't have the vector hats on my list there up there, remember that signs do go in and signs do come out. Okay? So what are we essentially saying here? What we are saying here is that if you're going 20 meters per second, and you're doing it in a circle of radius 10 meters, what you're also doing is you're covering 2 radians of angle every second. Okay? So we go ahead and we do the same thing on the final side. And just to spare you the suspense, we have 5 divided by 10, so that's 0.5. Now we're only covering a half a radian of angle per second. We're moving slower in the same circle. So we're not covering as much angle per time either. What's the direction of that? Is that plus or minus? Plus. It's still plus. It's still counterclockwise. And that gets to the heart of how different things are in the rotational world. If you look at these velocities in the linear world, it's completely switched directions. If we said that to the right was the plus x direction, now this is in the minus x direction. It's completely reversed directions as far as the linear world is concerned, right? In fact, the very thing that's bent that velocity into a different direction we call the centripetal acceleration. But in the rotational world, as long as you're circulating in the same pattern, the same direction, you're circulating counterclockwise, this is plus and this is plus, right? So this is still the same direction as far as the angular stuff is concerned. So we go ahead and we put in plus 0.5 here. Everything is going to be plus. Everything is going counterclockwise thus far. So how do we solve? Well, first I'd recommend ignoring this and solving for the time. What equation would I use? Number 4, right? The one that's missing. Oops, let me do that in black. You'd use equation number 4 for that. Put in those 3 knowns. The t is going to be the only thing that you don't know in that equation because alpha, the angular acceleration, is missing, which is good. Now you do want that too, so I would start from the same 3 knowns, but also solve for alpha and ignore the time. That way, if you messed up the time, then you don't have to worry about it, right? You have an equal chance of getting this. What equation would you use if you wanted to solve for alpha but ignore the time? Number 3. So let me just tell you what the results are. You don't need me to plug in algebra, that's not physics, that's just math. Okay? Once you know what you're plugging in and where you're plugging it into, it's no longer physics. Okay? That's just math. So let's find what we get. I'll tell you the results. From equation 4, the time ends up coming out to be 2.5 seconds. And alpha, from equation number 3, try this yourself at home, let me know if you don't get it. That comes out to be, can anyone predict what the sign of that's going to be? Negative. Why is it negative?
Because it slows the car down.
That's right, the car is slowing down. So if the equation will actually tell you it's negative, it'll come out negative, 0.6 radians per second squared. So even though we don't normally write it in the midst of the equation, we might want to now add back the vector hat because the signed input has produced signed output. And so again, just to remind you that since the car is slowing down, omega and alpha should be opposite. Omega was positive, so it's a good thing that our equation told us it was negative. If it hadn't, we would have had some kind of, we should have gone back and looked and see what went wrong. All right. So let's take stock of where we are. We've done most of the problem. We got the time, we got these, and these, and these, okay? So now we're ready to knock out the linear quantities asked for. And the first one, a tan, is going to be a snap because we have its angular counterpart, right? Once we have alpha, a tan is easy. Anytime you have the counterpart, you can easily switch over from linear to angular or vice versa. So we'll go ahead and put a tan is equal to r alpha. Let's do it. So we put our radius, that's 10 meters. We put in the alpha, and remember, we don't put in signs into this. So even though they're not commonly written with absolute value signs, remember that these equations don't mess with sign. All right? So let's see what we get. Well, we get 10 times 0.6, that's 6. And then the units appear to be meters radians per second squared. We can unceremoniously kick the radians out of there now that meters is going to slide in and hold down the units in the numerator. And then we have a tan. With smooth braking, alpha is constant, and of course its counterpart a tan is constant. We can add that, if we wish, to our diagram. How does a tan point relative to the velocity?
Parallel?
Parallel, yep. Which way? With or against?
With.
So it's speeding up?
Wait, no, against.
Against, yeah, that's right. It's slowing down. So we can write down a tan, 6 meters per second squared. It's always going to be against the velocity. So it's against the velocity at the beginning is to the left. And somehow it has to switch so that it's against the velocity at the end too. 6 meters per second squared is a tan at the end. Braking smoothly requires that you somehow make sure that there's an acceleration against your motion that's unwavering. Okay? That's the only way that the velocity will get chewed off in equal increments, and you'll brake smoothly. So now that I have a tan, you may wonder, well, what's up with the initial and the final? If you have the same, if you have smooth braking, you might say, aren't the initial and final accelerations the same? Well, a tan is the same, but the difference comes in acentripetal. So remember that both a tan, which is constant, and acentripetal, which is going to turn out to be not constant, have to go into the total acceleration. So let's take a look. We have to now work out acentripetal. Acentripetal is the unsung hero, which is what's going to cause the turn, right? We're not just slowing down, we're slowing down and also turning. And if you look at acentripetal, how much acceleration you need to hold a turn depends in turn on how fast you're going. Right? You can see that acentripetal is proportional to v squared. So if we're slowing down, v is getting smaller. What happens to acentripetal? It gets smaller too. So if v gets smaller, acentripetal gets smaller. So what that means is that the effort that is placed into holding the turn is going to be more at first and less later. So even though a tan is constant, acentripetal is not. Let me try to draw that in. Here, acentripetal initially is significant. You need to have a significant amount of effort to hold the turn. Later, A centripetal final is much smaller. If you're going slower, the amount of effort you need to hold the turn is much smaller. And so you can see that even though we've braked smoothly, and all the alpha and the A tan are constant, just the very fact that you're also going in a circle means that the amount of effort placed into holding the turn is changing, because the amount of effort needed to hold the turn is tied to how fast you're going. So let's work that out. Are there any questions before I clear a little space up here? Okay, so let's do a little bit of that. So let's work out A centripetal initial. So that's going to be V initial squared over R. Now I guess in full disclosure I should tell you that sometimes people express this formula not in terms of V but in terms of omega. So I can plug that in here as well, show you what that looks like. I could plug in V is R omega initial. And that simplifies to this. So if you see that anywhere, don't get too confused. That's just an alternative way of expressing the centripetal acceleration. You can take it as V squared over R or omega squared times R. Same thing. Okay? Either way, plug it in, you will get, let's see, I'll do it on this side, 20 squared over 10, I think that's 40, right? Be able to get that. A centripetal initial is 40. So a huge amount of acceleration needs to be applied to hold the turn at the beginning because you're going so fast. Work it out later. Let's see if I can do that. 5 squared over 10, so that's 2.5. So that's the part of my acceleration that's changing. And now I need to combine those accelerations, centripetal, with my constant A tan to get my total. Okay? So I guess I'll jot that down here. A tan was 6 meters per second squared at the beginning, and also that at the end. That's not the changing part. But if you're smoothly braking while going in a circle, your acceleration is not constant because of the centripetal part. So, let me show you how to do this. Now this is basically just combining vectors, vector components back into the whole. This is a skill that I mentioned at the beginning of the class, starting around homework 3, that if you don't get the hang of it, it's going to haunt you forever. So I can't keep going over it. Let me just briefly sketch it out. Let me do the initial point, this and this. What do? You place them head to tail, right? So I have my 6 meters per second squared. I place it head to tail with my substantial 40 meters per second squared. And here is my total acceleration, A initial. Okay, so how do I get the magnitude or size of A initial? Pythagorean theorem. How do I get the angle? Tangent or inverse tangent, right? So, same old stuff. Let me just tell you the result. A initial, use Pythagorean theorem on those guys. You get 40.4 meters per second squared. That's the size. Again, that's from Pythagorean theorem. And then this angle comes out to be, by inverse tangent, 81 degrees. Which is, of course, such a large angle, almost 90 degrees, because the centripetal is so big. In fact, this isn't really even drawn to scale, right? You have a tiny little centripetal or tangential component. If we drew this to scale, it would look more like this. Tiny, huge, right? So you can see that A total is going to be very similar in length to the centripetal, right? So it's not any surprise that it's almost 90 degrees because it's got a very small tangential component, right? Most of your effort at this point is holding the turn, right? That's what you have to be most worried about when you're going fast in a car. It's not can you brake, but can you keep the turn? So relatively little effort is being placed on actually slowing down at this stage, right? You have to devote 40 meters per second squared of acceleration, which means, of course, a much larger force component as well, to holding the turn while only a small bit of your resources is actually acting against the motion to start the motion slowing down. The other thing I should mention is that this angle is probably not the angle you would want. The reason why is that this angle is not very interesting. It's the angle between the acceleration and its centripetal component. What you probably want is the angle between the acceleration and velocity. So how would you get that? 180 minus 81, so this is 99. So this is 99 degrees from the velocity. So I basically did inverse tangent to get to 81, which is easier, and then I subtracted from 180 to give a much more interesting angle. Remember, we said last lecture that when your velocity and acceleration make an angle of greater than 90 degrees, you will slow down. Right? You're going in a circle, but slowing down. So the acceleration is both inward to hold the turn, but also against you to slow you down. So the angle is going to exceed 90 degrees. In this case, not by that much. It's only 99 degrees, because most of the resources are still being used inward to hold the turn, while relatively little is being used at this stage to slow the motion down. Okay, are there any questions on that? Okay, so similar process for this one. We have that we have a tan, 6 meters per second squared. We have now the amount of resources we need to use to hold the turn is very little. So A final is like this. Now most of our effort is actually on the slowing down part, and the amount that we have to use to hold the turn is relatively little. So notice that they switch roles. Of course, A tan has been constant, but the effort that is needed to hold the turn, A centripetal, is huge at first, and then very little later. Maybe you've experienced this while braking, right? If you're trying to brake while taking a turn very fast, you're mostly worried about flying out of the circle. But if you're trying to accelerate, if you're going very slow, then you feel the backwards and forwards acceleration, the tangential, much more strongly, right? So once again, inverse tangent and Pythagorean theorem are going to be your friends. You probably want to measure the angle between the velocity and acceleration. And let me just tell you the answer, make sure you can get these. The final acceleration here will be 6.5 meters per second squared, and the angle, after subtracting from 180, is 157 degrees from the velocity. That angle has grown significantly, of course, because now it's more about the backwards force and backwards acceleration, A tan, and not so much about holding this inward. Okay? So notice that the acceleration is very different at the beginning and at the end. The size of the acceleration isn't the same. 40.4 and 6.5 are not different, are different sizes. The angle is different. We go from a 99 degrees to 157 degrees from the velocity. But all of that difference is on the centripetal side, right? The tangential side was exactly the same. 6 meters per second squared against the motion. The difference was all in the effort needed to hold the turn changed. Now what have you guys do on homework is a discus thrower problem, which is the opposite. Instead of slowing down while going in a circle, a discus thrower speeds up going in a circle. If you ever tried to throw anything heavy like that, you know about this allotment of resources. At first, the hardest thing to do is to get it going like this. So at first, A10 is your hardest thing. Your amount of effort needed to hold this thing is very little, to hold it in a turn. But when you start spinning faster and faster and faster, it feels like it's pulling your arm out of its socket. Okay? And the reason why is that now that it's going fast, the effort needed to hold the turn is tremendous. Okay? So the thing that varies here is the acentripetal. And that's the only reason why the initial and final accelerations as a whole are so different. Even if we're talking about smooth changes. The smooth part just implies that A tan and alpha are constant, but by virtue of the fact that we're going in a circle, acentripetal can change significantly. In fact, it's tied to the square of the speed. So there can be amazingly large differences in the centripetal acceleration when you change speed. For instance, if you go twice as fast, you'll need 4 times the centripetal acceleration. And so no wonder we go over to the angular side, right? Things are easier on the angular side, right? If we get to assume we go in a circle, and we don't have to worry about the ever-changing demands to go in a circle, then as long as we speed up or slow down smoothly, we can be guaranteed that alpha and A10 are constant. When we come out to the linear world is meant to describe all sorts of different motions, and so it's not particularly designed to work with circular motion. And so there we have to acknowledge, again, that going in a circle is a privilege and not a right. And if you want to go in a circle, you need a certain amount of acceleration called acentripetal to do that. And if the centripetal acceleration is in turn tied to your speed, then if you want to speed up and slow down going along a circle, then the demands of how much acceleration you need to hold that turn change all the time. So you can see that when we went over to the linear world, which is not really tailor-made to deal with this stuff, it got a little bit more complicated. Are there any questions on this? Okay, so you have one of these everything but the kitchen sink things on the end of your homework 8. That's the discus thrower problem. This is kind of meant to parallel it without doing it exactly for you. This right here, if you want to mark it off, is the cutoff between homework 8 and 9.